Okay. Should we? Okay. Well, good morning, everyone. So it's my pleasure to have the first panel getting started. As Jorga said in the morning, the workshop has three distinct themes: signal processing, communications, and networking. And we are going to start with the signal processing theme. And once again, I guess belated 66th birthday. I guess Jorga says that. I'm glad we are not having it in February though. But it's beautiful weather, pleasure to be here. The purpose of this panel is to kind of reflect in the past of signal processing. The title is starting from 1980s because that's when Jorga started his academic career. But some of our panelists will even talk about things before that. We'll talk about the past in terms of impact on research, education, mentoring, and so forth. And we'll also then look at or try to predict what the future might hold. Before I get started, I just want to introduce our panelists who don't really need introduction, but I just want to say a few things about them. So let me just get started with, on my right, Professor Louis Scharf. He is a research professor of mathematics and emeritus professor of electrical and computer engineering. He's also affiliated with the Department of Statistics at Colorado State University. His research focuses on statistical signal processing and machine learning with applications in radar, sonar, communication, and so forth. He has authored several textbooks, including Statistical Signal Processing, Coherence in Signal Processing, and Machine Learning. He was awarded the Jack S. Kilby, IEEE Jack S. Kilby Medal for Signal Processing in 2016, and the C.F. Gauss Education Award from IEEE Signal Processing Society in 2021, and he's a Life Fellow of IEEE. Next, I have on my, I guess, again, right, is Jitendra Tugnait. He is the James B. Davis Professor of Electrical and Computer Engineering at Auburn University, and his research focuses on statistical signal processing and machine learning. He's a fellow of IEEE and has held numerous editorial roles, including associate editor of the IEEE Transactions on Automatic Control and a senior editor of IEEE Wireless Communications. Next to him is we have Professor Vincent, who is the Michael Henry Slater University Professor at Princeton University with research interests in information theory, statistical signal processing, machine learning, network science with the applications in wireless networks, energy systems, and related fields. Among his publications is the recent book, Machine Learning and Wireless Communications, published in 2022. He's a member of the U.S. National Academies of Engineering and Sciences, and he received the IEEE Alexander Graham Bell Medal in 2017. Next is Dr. Sanyogita Shamsunder, who is the Chief Operating Officer at NextG with over 2 decades of leadership experience at companies like Verizon and Google. She has led groundbreaking wireless initiatives, including the launch of the world's first large-scale 5G network and smartphones. She has managed significant budgets and spearheaded 5G technology development at Google's Edge Networking and Verizon. She has an MBA from Wharton and a PhD in math and statistical signal processing from University of Virginia, and she advises tech startups and also is involved in volunteering for STEM education and women's sport initiatives. And last but not the least, we have Professor Petar Djuric, who is the SUNY Distinguished Professor, and Savitri Devi Bangaru Professor in Artificial Intelligence in Stony Brook. He has served as the chair of his department, and his research focuses on machine learning and signal processing. He's a fellow of the IEEE and EuroSIP. He received the EuroSIP Technical Achievement Award in 2012, and he was the founding editor-in-chief of the IEEE Transactions on Signal and Information Processing over Networks. So I just want to welcome all the panelists and look forward to a lively discussion. So the first, the way it's going to work is we are going to have a lead panelist for each question. We have about 5 questions, one for each. The other panelists will then add their thoughts, and we are also looking for interactions from the audience, so you can also add to that. So we started with the first question, which is going to go to Professor Louis Scharf. He's going to lead us off. The thought is about over the last 40, 60, or whatever number of years that you want to talk about, how has the definition of signal processing evolved? What is the meaning of signal processing? If you were to define it in 60s or 80s or 2000 or today. And so we'll kick off with Professor Scharf.
Yeah, thanks, Waheed. Okay, I don't want this to sound too much like a personal journey or remembrance, but I will use a few anecdotes from my own professional experience. How many people have heard of Ted Hoff? Okay. Well, in 1980, I was the technical program chair for ICASP. It was the 5th ICASP ever held, 1980 in Denver. And we invited Ted Hoff to give one of the keynote speeches. And he arrived in Denver and he talked about microprocessors. Why did he talk about microprocessors? Because he invented the microprocessor. But this is a signal processing meeting. Did I forget to tell you that Ted Hoff also invented with Bernie Widrow the LMS algorithm? Okay, so this makes the point that nothing we talk about here in this meeting would make any sense whatsoever if it hadn't been the kind of hand in glove march forward of VLS computing technology, VLSI technology, Moore's law, and what you might say is applied harmonic analysis, applied linear algebra. So these fields have marched together to give us all the wizardry that's been talked about this morning. Okay, so I've broken my remarks up into 3 two-decade periods from 1960 to 1980. What was signal processing? I say here that signal processing was never DSP, but DSP was signal processing, and DSP birthed statistical signal processing, which is a marriage of DSP and detection, estimation, and time series analysis in time, in space-time, in frequency wave number space, in fast time, slow time, in channelized representations of signals, and channelized synthesis of signals. This is where Georgios and his students work. Okay, so we might say the 60s to 80s were the 2 decades of Kalman filtering, which evolved into Gaussian sum filtering and particle filtering. The FFT revolutionized DSP for data analysis and filter implementation. In a very general sense, Fourier analysis evolved to the Gabor transform, short-term Fourier transform, wavelets, and Filterbanks. Just as an aside, after I completed my studies at the University of Washington in 1970, my colleagues at Honeywell's Marine Systems Center delivered a rack of hardware to the Naval Underwater Systems Center to compute an 8-bit, 256-point complex FFT in 0.4 milliseconds. We've come about 6 orders of magnitude from there. So that's why the stuff we talk about makes sense, has currency, has meaning, is because it's so tightly coupled to what we can actually do in computing hardware. DSP in this time period was filter designed to approximate analog filters. That's what it started out as. It was linear prediction and AR modeling for model identification, modal analysis, spectrum analysis. It was lattice structures for speech synthesis. And these lattice structures gave us a way of getting our minds around order determination, dimension reduction, if you like. And order determination, dimension reduction remain standout problems in many branches of statistical signal processing. In the papers that Georgios has done where he extends principal component analysis in Euclidean spaces to principal component analysis in function spaces. And the work they did on precoders and equalizers, we always had an order fitting rule. Okay, maybe it was linear and quadratic functions, the data, sufficient in linear prediction in the multivariate normal model, but insufficient in other models that motivated Georgios to take an interest in higher order statistics. 1980s to 2000s, these years saw comprehensive development of data adaptive signal processing. We call it adaptive signal process. It's data adaptive signal processing for filtering, linear prediction, channel equalization. Adaptive beamforming was and still is a huge application in radar and sonar. Detection and estimation in radar and sonar, remote sensing, subspace fitting, subspace methods. We now have a comprehensive theory of matched and adaptive subspace detection and estimation theory with applications in many, many applications. It was the era of music and esprit, advanced modal analysis, fast algorithms, time frequency distributions, and a misplaced angst over the negativity of these time frequency distributions. Filters, filterbanks, wavelets, subband coding, and related. 2000s to the present, and I'll terminate here, and I'll have a little less to say here. This appears to be the era of frames, sparsity, compressed sensing, signal processing on graphs, and other geometric structures. Signal processing with non-Euclidean constraints, new application areas, self-driving cars, recommender systems, computational imaging, phase reconstruction, and so the list goes on. I might remark here that, as Bhaskar made very, very clear in his talk, sparsity is not a story in compressed sensing. Compressed sensing is a story in sparsity, and there's a difference. Okay, with those remarks, I'll stop and hope that the rest of the panels fill in all the things I left out. Thanks.
Okay, so thank you. So we have two mics, and we will start with the panelists, adding more to basically what is or what was signal processing in your view going from 60s, 80s. Like, let's take those four time periods in time. Petar, are you starting?
Okay, I can start first. Yes. So one thing that Louis made or provided a very comprehensive overview. One thing that he did not say is Bayesian signal processing. So Bayesian signal processing was hidden until about 1990 because Bayesian signal processing requires a lot of computing power. But as soon as computers came about and one could use them on the desktop, so that was a time when MCMC, particle filtering started to become methods that were adopted by many around the world. So this is one area also that I think could be mentioned as part of the history of signal processing in the past 30, 40 years.
Actually, I don't have much to add except for the wonderful retrospective on signal processing, Professor Scharf. Nobody but you can do that, I guess, given your experience. So that was great to go through that. But I think the story that emerged for me in this is that the people in the signal processing world make every problem their own. Every problem becomes a signal processing problem. So I think in that sense, we are always open to trying out new things. The great thing about processing signals is that it is people identify with the problem statements many times, and it's what draws in a lot of interest. So I don't think I think it's hard to say where we will go from here. The past performance is no indication of future success, but I feel like there is continued interest and continued opportunities. So that's all. Okay. I got my phone.
Yeah, so certainly everything is signal processing in one way or the other. That's a good point. And Louis, I think it's hard to add much to what he said, but I would say that one point that came out, I think, in Louis' comments is that, signal processing has always been kind of driven by the constraints of the hardware. So the things that we focus on are the things right at the edge of the hardware, and we get better and better hardware, faster computers, and so forth. The old problems are not problems anymore, and new problems come up. So that seems to be a trend of what you were saying, Louis, if I understood it correctly. So, good.
Nothing to add.
No, nothing. Okay. So I guess time to turn over to audience. Any questions or additions to what was said?
Waheed, may
Oh,
I would like to add one comment.
Yes.
there was one ICASP MOS that was here. I believe it was in 1993. I was then assistant professor, and I remember a conversation I had with my colleagues, and the question was, is signal processing dead? Because we felt that everything that was there to be discovered was almost discovered, and we are hitting just walls and walls. How wrong were we?
So any comments from the audience or any?
Just make one comment about Louis. Thank you for your wonderful overview. You mentioned Ted Haag. So Intel 4004 was Ted Haag and Frederico Fagin, who I both got to know fairly well. But the humorous part here was that I think 2019 was the 125th anniversary of E department. So we recognized the 4 major inventions which changed the world. The first was the Tristra, Waheed brothers, which I think they say won the war for us in the Second World War. The second was Marty Hellman's public key encryption, right, which along with Diffie. The third was MIMO, was deservedly so. And the fourth was most stranger, which I haven't figured out, was the microprocessor, Ted Haag. So I asked Ted, should Stanford claim that? Because that was done at Intel. So he didn't quite give me an answer. So Stanford should have to explain that. Thank you.
Any other follow-up questions on that theme or additions?
It's too bad he didn't have a mic.
Yeah. Yes, Moss.
So I want to ask, we perhaps Vince, since interaction on this, briefly to comment on what Petar just mentioned about signal processing being dead. Obviously, one of the concerns that continues to come over and over is that machine learning and AI have taken over. Signal processing, is there signal processing anymore with all of these things happening and getting all the attention? And I happen to be looking at an old transaction for reasons that become clear tomorrow. But so the 1986 transaction.
I think you should have this so people can hear you. And it's too bad that Paul Raj couldn't be. How many people heard Paul Raj?
No, but on the recording. So, let me just repeat again. Obviously, within the signal processing community, there is considerable angst and conversation. Actually, Ali, you were on a panel discussion last year, the history of signal processing panel, that discussed this somewhat. Is the dominance of machine learning and AI, broadly speaking, well beyond signal processing and everybody else. So the question always comes up with signal processing, boy, we've been doing a lot of these things for so many years, but now nobody recognizes us, nobody connects signal processing with AI and machine learning and so forth. So what do? So I happened to, so now I go back to what I was talking about. I was looking at some old transactions of the Acoustic Speech and Signal Processing Society. Believe it or not, back in 1986, the transactions for the society, which was called the Acoustic and Speech Signal Processing Society, was published every other month. It wasn't even published on a monthly basis. So that tells you something about, first of all, there was only one transaction for the society, and it published every other month. So that tells you about the volume of papers. So going to that, and I was looking at the back of one of those transactions from 1986, and it reminded me of the workshop in 1986 on signal processing, the signal processing workshop, and this is where I'm going to hand it off to Louis because he was there. And it had a list of topics that they were asking for papers and so forth, and one of them was AI and signal processing. This is nothing new. It's nothing new for signal processing. So, Louis, back to you. You were there.
Was this the meeting in Boston?
Yes.
So,
No. This is the signal processing workshop. It was that Lacoste was the general chair.
so actually, if I may interject, actually, that is exactly one of the questions that we had. So we'll probably switch the order if that is okay, right? And Vince was going to lead that question.
Good.
So if that is okay, Louis, is that okay with you? Yeah. And then we'll switch the order of questions, and we'll start since Moss asked that question, right? And then we'll start from Louis after that. Yeah.
Okay, thanks for the prompt. First of all, you asked the question, is signal processing dead? I mean, you're at ICASP, right? 4,000 people. I think that's a pretty good sign that it's not dead, right? So Waheed admonished us to stay within 2 minutes. So I'm going to try to do that.
We're already out of that trip.
I'm going to try to do that. But so first of all, I just had a few comments, and I'm hoping that that'll be filled in by my colleagues here. But I just want to say a little bit about, sort of the way I look at AI and ML now in the context of signal processing. So first of all, my corners of signal processing have traditionally always been model-based. I mean, communications and things like that. Whereas other areas like speech and image processing, I think, have been more data-driven in general. And even things, model-based areas, have adaptive versions, right? So they're also data-driven in a way. And of course, as was pointed out, the idea of data-driven things like neural networks and so forth, it goes way back, right, in the field. It's not new. What's new is just the capabilities of the computers and the availability of data. So scale and scope are the main difference, right? They've greatly expanded. And some of the newer methods that people use, like transformers, deep neural networks, autoencoders, I think these are naturally part of signal processing. They come right out of our toolbox, right? On the other hand, other things like reinforcement learning, I think you might say come out of the control systems toolbox. So we don't really own, I don't feel like we own AI and ML. It's really too big of a tent. But I think we own part of it, right? And I think we should embrace that, and we should, stake out our ownership of that. But we shouldn't expect to own the whole thing. But I don't think it's going to do away with signal processing. I mean, it's like, it's enhanced signal processing, if anything. So that's my 2 minutes worth.
Oh, appreciate that. Okay, thank you. So I think, Mark, you want...
And I just make one
Yes.
correction. Sorry, Louis, to put you on the spot. This gentleman who was at the workshop. So I need to hear from him.
Okay, we can start with Louis, I guess, and then so the question, which was on our original question list, so I presume every panelist has some thoughts about that, which is, the intersection of machine learning, AI, and signal processing. It was like the last question, which we have moved it forward, right? So what do we want to claim? What do we not want to claim? And do we really need to say that we own everything or not, right? Vince already kind of alluded to some of that, but yeah.
I don't know. Machine learning is a very, very clever term. Too bad we didn't think of it. Signal processing, people have had a field day forever mischaracterizing us when it's in their advantage to do so. In other words, aren't you the men and women who build front-end analog filters before we start doing something else? Actually, mathematicians have much higher regard for signal processing than some of us have for our own discipline. So embrace it. I think what's behind all of this is that, correct me if I'm wrong, if you're an educator and you'd like to teach your courses in signal processing, you don't get enough students because students are taking optimization theory for machine learning, or they're taking matrix methods for machine learning. They're taking this, that, and the other thing for machine learning because it looks like the jobs for students coming out of disciplines like ours are going to people who call themselves machine learners. Now, I'm very much interested in listening to Dr. Shamsunder here because you hire people. But I think our problem is a naming problem or a marketing problem, something like this.
Yeah, go ahead.
I was involved about maybe less than 20 years ago, chairing a committee by the Signal Processing Society to look at the name of our society. Should we change it again? And we were debating for maybe 1 year. We all agreed that signal processing was, as a name, was too narrow to describe what we were doing. But 50% of our membership wanted to keep the old name. 50% wanted something else. I personally was in favor of a name that I will share with you. I wanted to call it Signal Science and Engineering. But we stayed and we're stuck now with this name. My personal opinion is that at the heart of machine learning and AI is signal processing, but not many know this, except maybe experts. I'd also like to share with you one other anecdote, how life is full of surprises. In year 2003, I was attending ISCA's conference in San Diego, and there was a panel of program directors of various funding agencies. And one of the first speakers came out on the stage and said something like this. If you plan to submit any proposals on neural networks, be warned, it will not be funded. We are tired of neural networks proposals. So only 3-4 years later, things turned around completely, and guess where we are today?
I agree. I think the term is great, and it's a good marketing tool. So you own it, right? So I call myself, I have 25 years of machine learning experience. So I think a lot of that which is true, which is not false. But going back, I mean, to the original question, is it dead? I mean, I think. I don't know that it is dead. I think if you are a good discriminant person in the industry, you understand what skill sets this particular candidate may have and what type of courses that they have taken and so on, and projects, and not necessarily be swayed by some of the jargon that you see. Jargon is probably I'm being unkind here. The words in that are prevalent today. So I don't know that it's necessarily, at least for me, speaking for myself, I don't know that I'm swayed by something like that. Okay, sorry.
Yeah, I'll just make a few comments on what Moss said about the AI in the 80s. I worked for Exxon Production Research from 82 to 89. At that time, a lot of vendors used to come, a lot of outside people would choose to come, and they were promoting expert systems. And to go along with the expert system, but they were trying to sell you list machines. So AI has been used and tried to sell hardware and other stuff for a long time.
So I guess that is a topic that perhaps is very near and dear to many people. So are there people in the audience who would like to add further, or perhaps pick up on any of the thoughts? I guess we'll yeah.
I'll say that the history of signal processing has been throughout the decades. Signal processing has always brought rigor and discipline into things that people try to do, some heuristics and some things and don't understand what they're doing. I mean, I remember many years ago, like as undergraduate student doing an internship and programming assembly on some 8-bit microcontroller, and just everybody would like do a moving average filter or something to reduce the noise, but I didn't know what I was doing, or everybody can take an FFT and say, oh, there's a spike, but people wrote books on spectral analysis to understand what's going on and what are the limits and so on. So if there's going to be discipline and rigor in these ML models and this very complex, another level of complexity of, as Ali was saying this morning, going from individual components to just trying to design whole systems, which are hard to understand. I think this community is well equipped and will make very significant contributions in moving this whole AI technology forward, like real progress on AI, not just heuristics, and trying to just see what works. Thank you.
Yorgos, you wanted to add?
Thank you. Thank you. I just want to stress the comment on the naming. I think the CS people oftentimes enjoy renaming known things like autoencoders that you mentioned. For me, it's nonlinear PCA, right? Or they have beautiful, even better names like knowledge distillation. And it's nothing more than dimensionality reduction or multi reduction. So I think the best ambassadors of signal processing to machine learning community are people like the three expert speakers and the headline speaker, Ali, Yoram, Bhaskar, PP, they demonstrated how signal processing tools can enhance the machine learning community and knowledge. I think that's the best approach we should pursue.
Any other comment about that?
I have a question for Iman. I got the feeling we're a little too apologetic.
Hold on, Alejandro.
The question that I have for you is this. I mean, you were kind of apologetic in your defense of signal processing, which I don't think we need to be. I mean, like one of the most important developments in deep learning are convolutional neural networks, right? Which are convolutions. So, it's like a right down our alley. Now, the thing that I think I would like you to elaborate is how do you make this into an opportunity, more into something that we need to defend ourselves?
And we have to be careful not to say that we have to be careful and not say that X, Y, Z in machine learning is just A, B, C in signal processing. That puts us on the wrong side of the argument. We have to embrace machine learning. I want to comment about what Mikhail said, and I agree with what he said. And in things like radar, sonar, geophysics, hyperspectral imaging, imaging of all sorts, performance bounding, performance analysis is an honored enterprise because we like to build things and say the probability of false alarm is 10 to the -6th, and it really matters. But a lot of the problems in machine learning, it doesn't really matter if you make a false alarm. So there are a lot of problems in machine learning that are quite different than the problems in signal processing that have energized this exquisite performance analysis and performance bounding. So I don't know to the extent to which we can tie our future to exquisite analysis. I'm just asking.
Thank you. Okay, so we are kind of halfway mark in terms of our allotted time, but I was told that some of us would enjoy the discussion so much that we can delay the lunch. So hopefully that would be going on. Okay, I just want to piggyback on what Louis said. I think my personal feeling is, even though I'm not a panel expert, I'm just like a moderator, but I just want to say that I think part of the distinguishing feature could be, right, that we own that what do we bring to the table, rather than saying AI ML is what we are doing, right, is what do we bring to the table. And what we bring to the table is analytical tools as well as understanding the systems better. I think the systems aspect of the problem, that's my personal view, sets us apart. But moving on to the next question, which is probably going to be a little bit more challenging, right? We have thrown out a number of ideas. We have said we have been doing this. Louis started from 1960s. The question is if, and this is the lead, we'll start with Jitendra, right? Which is that if we have to, each one of the panels, but if we had to pick one key contribution in each of that era, right? Now not a laundry list of all the things we have done. One key contribution in each of the era that signal processing has given to the society, right? What would that be? And we'll kick off with Jitendra.
Okay, the question I was given earlier was to start with higher order statistics.
Right, so you can start from there, yeah.
And I'm going to start with that because that's where my association with Yorgos starts. So as I said before, I was working for Exxon Production Research 82 to 89. And one of the big problem they have is the seismic deconvolution and their newfangled methods of vibrosize, which is chirped signal. So that makes it non-minimum phase. So there was a lot of work going on at that time, but it was not explicitly called higher order statistics. As Bhaskar mentioned, one of the Donahoe's paper way back in, I think, 1981 in one of the conferences, which he wrote when he was doing his summer internship with Western Geophysical. And his mentor wrote a paper way back in 1978, and he called it Minimum Entropy Deconvolution, published in Geoexploration. And it's algorithm, some simulation, real application data, So Donahoe wrote that paper to explain, and again, he used the word minimum entropy deconvolution. So that's a class of approaches tied with what was going on in communications, constant modulation algorithm, self-recovering equalization by John worked on the constant modulation stuff. So those class of stuff, algorithms which are based on inverse filtering or deconvolution were not explicitly classified as higher order statistics, while they used it implicitly quite a bit. Then came a paper in 1982, which by Lee and Rosenblatt, analysis of statistics. But when I saw it as they were good. They presented a paper in Exploration Geophysics Symposium. So I saw the abstract and I was intrigued. My friends were intrigued. So I started to work on it. Then it turns out Jerry Mendel and his students were also starting to work on it. So. And then Nikias was working on bispectrum from the nonlinear interaction point of view. So those two guys, Mendel's group and Nikias' group, they heavily started to promote it, do some workshops, do some special courses and stuff. So during that period from middle 80s to middle 90s, that just took off, essentially being motivated by blind equalization, okay? That stuff lasted for a while, but it turns out in communications, you can do stuff at the transmitter, you can do pre-coding, you can do Filterbanks stuff, whole bunch of stuff. So you really don't need higher order statistics. So it influence on the communications problem has not been that much in the sense, except maybe for DoD applications where you can't manipulate the transmitter side, you just snooping. So there it may be very useful. But as Bhaskar mentioned his paper, Donahoe's paper, Donahoe didn't use the word sparsity in that 81 paper. They were using the word spikiness. So they wanted the deconvolved stuff to look spiky. But later on, he turned it into sparsity. Okay, so from my point of view, the single biggest thing to come out of the higher order stuff is basically the source separation or independent component analysis. To do that, you need, so it's not higher order per se, it's just you need some sort of non-Gaussian stuff. So it's a non-Gaussian part that comes out of the higher order stuff. And that's pretty useful for doing source separation and independent component analysis. And I'll stop there.
Yeah, okay, thank you. Yeah, so the rest of the panelists can pick either one of those themes or comment on each one. What do you think is the major contribution in each of these eras, and going even further back from where Louis started, up to you?
Yes, well, I don't know if I can divide it into eras, but I would just say, I mean, the point about, the question is really, what's the biggest impact on society, right? Yes. So I would say, you know, regardless of the era, and probably this does break down into eras in a certain way, but I think, you know, certainly the contributions of signal processing to wireless communications has had tremendous impact on society. Everybody here is looking at their phone. Everything you want to do, you can do on your phone pretty much. And billions of people their lives have been changed by cellular communications. And signal processing has been a huge part of that. Paul Raj mentioned MIMO, which has, allowed us to have high-speed signal processing. I would say the other thing, and I don't want to exclude other things, but the other thing that came to mind was image analysis, right? Pattern recognition. I mean, everywhere you go now, they take a picture of your face, they know who you are, whether it's good or bad. I think that's really a legacy of signal processing that we're living with now, and it has really a huge impact on society, and will continue to, I think, in many ways. So to me, those two really stand out. Which methods play into that, I don't know. Maybe all of them do, but that's in terms of applications. I think those are the ones where signal processing really has affected society in big ways. So.
Thank you. Sanyogita?
Another application, yes, wireless and image processing. So I think the other one that is, maybe even started even earlier and kind of was the genesis of signal processing is speech and audio. Yeah. Right? That's one of the big areas, and I feel like that's again coming back to be an important area. There's been a lot of work in image processing. It has gotten a lot more attention than I feel. Maybe I'm biased in speech and audio. And now with the latest version of whatever, multimodal systems and stuff like that, I think there's a lot more opportunity for speech processing to be back into the mix of signal processing.
I'd like to mention two application areas where signal processing has played very strong, that has made very strong impact. Obviously, one is defense, and the other one is healthcare. We all know that today so many diagnostics are done based on just in the background signal processing methods.
I want to go in a slightly different direction and speak to the intellectual foundations of what we do. And so I think the important thing about the impact signal processing has made is to demonstrate what a tight coupling between digital electronics, Moore's law, and mathematical methods of harmonic analysis, and you might say applied linear algebra, what this coupling has enabled us to do. One of the things it's enabled us to do is look at almost any problem as a channelization problem. Channelizing in frequency time, channelizing in subbands. Think of all the ways you channelize and process in channels using the latest advances of Moore's law. Maybe we should talk about signal processing on the basis of our intellectual foundations, which I just tried to characterize.
Thank you. Okay, so audience turn. Additions or John? Can you get the mic here? While we get the mic, I just want to say that my student, when he was applying for internship, he said Amazon, when they asked for internship, they asked for, have you published in conferences for speech? And they put ICASP in one of the conferences in addition to ICML, NeoReps and stuff. So just wanted to piggyback on the idea that speech and ICASP, they still are one of the premier conferences. Please, John.
Well, the two of you and about what may have covered the points I was. This microphone is not wonderful. I've ascertained I'm not the oldest person in the room. We're not going to go to that, but I'm pretty old. Okay, and I want to point out, if you go back and look at transactions of audio and electroacoustics in the 60s, don't underestimate the impact of the FFT. 1964. The mathematical beauty of it, everybody wanted to write papers about the FFT. And it also took something that was very computationally complicated at the time, the DFT, and turned it into something you could actually do on a computer at least at audio rates. It was revolutionary. a lot of the theoretical work was going on how do I make a Butterworth filter into a digital filter, okay, but the real impact in terms of Louis' channelization was now I can do it, and I can do it spatially, I can do it temporally, I can do it whatever. It really made a tremendous difference. And let me also add that in the 70s, when I try to think of what the biggest thing going on, at least in the commercial was audio. And why? Because that was the most computation you could do. If you think of what A to D converters could do at the time, you were really lucky to get 10 kilosamples a second. Okay, and so the 70s were all about trying to make digital signal processing practical, but the highest rate we could do it practically at was audio. I'm going to ask a question like that Louis asked at the beginning. How many people in here remember the Speak and Spell? A product from Texas Instruments called the Speak and Spell, the first commercially successful DSP-based product. And it opened eyes to the world, at least to us, that you could make these things practically. It opened the eyes to the commercial world. They could make money at it. Okay, and it was worth investing in that kind of semiconductor technology. You know, speech synthesis, speech generation, that kind of thing. Anyway, it's a fascinating time. I won't take any shot at the 1980 and beyond.
Andreas, so just get the mic is a little bit finicky, so maybe hold the receiver.
Yeah, I wanted to come back to something that Louis said in the beginning, machine learning and signal processing. And, one of the most impactful, I think, innovations that happen within our society is the code-excited linear prediction, right? I mean, it's an enabler in terms of compression in cellular communications. I remember in 1985, Vishnu et al. Came in and gave the paper at the time, and it took them overnight to train a code book, right? Machine learning started quite a bit in our society, at least, with the training of code books, right? And some of that work also goes back in the late 70s, too. But, back then, the algorithm was presented. Everybody was very skeptical because it took them overnight to process 10 seconds of speech, and people came out saying it would never happen. And it happened in 1988, just 3 years after, because of developments in DSP chips. So I just wanted to bring that up.
Right. Ali? Yeah. So.
Okay, thank you. Very, very important. Historical remarks are very important. I just want to comment on signal processing and AI. Of course, we can talk about the history of it and how the history of these two domains are intertwined, starting from many, many decades ago. But I think moving forward, we have an opportunity. Okay, and I see an opportunity in two ways, right? No matter what we say, machine learning and AI is there, right? And the public at large is paying attention because you see all these fancy tools, all these fancy apps, right? But I see two opportunities for us to show that this community is very relevant to this domain moving forward. One of them, all of us know that all these AI tools that we are using today, including the most sophisticated, right, they are highly imperfect, right? If you just try to play with some of these ChatGPT and Google Gemini and other similar tools, you are going to find out that they are not perfect at all, right? So how do you make these systems reliable? How do you make them understandable, explainable? This will require lots of system analysis, right? Analysis that this community here is very good at doing. I see that as an opportunity for us to try to help these tools become, have a stronger foundation than they have today. But there is another field that I think where we can also prove that we are very useful. Just like in the intelligence community, they talk about counterintelligence, right? I think in the AI community, we can develop something called counter AI.
And what do I mean by that? These systems need to be controllable. They are going to become very intelligent, right? Very intelligent between quotation marks, right? They can do lots of good things, but also they can do lots of bad things. And we need to have a theory that allows us to counter that effect. So I'm of the opinion that this community, right, we could devise a topic that relates to counter AI tools, okay, so that you make these systems controllable, and we are very good at that. So these are just two examples of things that I see where we can contribute moving forward. Okay.
Thank you. So I guess we'll move. It's kind of related to the topic that you were having, but we'll move to Sanyogita. Question for you, right? Which is that now switching gears from society and contributions to basically education, mentoring, and all that. So how has, in your opinion, the signal processing, education, mentoring, and their placement in the industry evolved over the years from, again, we are starting the history from 80s, but you can go back even further back if you want. How has that evolved, and going forward, how might that change, or do all of us, our students, have to be relabeled, AI specialists, right? So we'll start with you, and then go on to other
panels. I'm sitting amongst academicians who have a better idea about how signal processing is taught today than I'm sorry, I'm a little ignorant in that. But let me go back a little bit in my own journey of why I decided to study signal processing, and that may be how people get motivated. I don't know that that's a you can generalize it, but maybe it's at least a data point, and maybe a few data points based on my experience talking to people. So I started my undergraduate degree in electronics and communications engineering in India. And the first class was semiconductors, which I hated. So the reason I joined ECE was because I liked math. And they said, well, you can't do an undergrad in math. You won't get a job. So do engineering. And of all the engineerings, ECE sounded the funnest. So come the final year is when I took my first class in DSP. So this is many, many years ago. I'm not dating myself, but you can, many, many years ago in India, this was the fourth year class. DSP was a fourth year class. And that's when I really enjoyed, being in this field. And part of it was motivated, again, by practical applications, right? Like it is so intuitive, and it is so relevant to our day-to-day lives when we talk about processing speech signals, image signals. At that time, wireless was not, a discipline at all, but communications maybe, but it was like more esoteric, right? But being a part of biomedical signals, those were all the interesting applications that motivated at least me. And when I talk to many people, that's what motivates a lot of students. So fast forward, I decided I'm going to do a master's, and Yorgos convinced me to come and do a PhD at UVA. And while the rest of my cohort went into semiconductors, VLSI, and so on, me and my husband are the lone wolves in communications still. And then I went to teach. And I was asked to start a new class, a first-year class in fundamentals of electrical engineering. I don't know if it's still there at Colorado State, Louis. But that was the inaugural class that I put together. And of course, I'm biased. So all the examples that I put together were based on signal processing. But the amount of interest that got among the students was fascinating, right? People were excited about being able to play with this and build stuff. So this, clearly there is interest, and it's not going to be everybody's going to do this, right? There's always a special set of people who are interested in something like this, and that may be enough for us to move forward and contribute to this discipline. And going back to what Ali just said, so I don't do day-to-day this anymore, but I am quite interested in sometimes looking at details of stuff. So I went and looked at the Transformers paper to see if I can see a proof of something. But I'm waiting for one of your students to come up with a proof of why this works. and what hallucinations, how can you explain hallucinations better mathematically or even solve, maybe explain, bound them? And what does explainable AI mean? There's a lot of talk about explainable AI. There are startups doing explainable AI. But when you dig deeper, it's really explainable in a very, very narrow context. It's just a, I guess, footnote that they put in there. So long story short, I don't know how it has changed. I mean, are we teaching signal processing earlier? Are we teaching more generalized techniques? Are we making it interesting enough for a diverse? I mean, that's another important part for me. I see a lot more females in this discipline, but I still don't see that at the topmost level. So I think I'll be making it interesting enough and relevant enough for students, for the younger population coming into education. I think I would worry about that.
Thank you. Okay, we can, Jitendra, if you want to start off from the rest of the panel, and we'll move on to your right.
Okay. I think whether something is classified as signal processing or not is a function of where the initial papers get published. So where the pioneering papers and ideas get published, so if they get in the NIPS or ICML, or then gets classified as AI/ML. If it gets into the signal processing transactions, it gets a different label. If it gets into computer vision kind of stuff, or PAMI, or information theory. So I see a lot of faculty members in our school in computer science departments. They hang out with IEEE conferences and transactions, but they take the lead in AI and machine learning, and they're all sitting in computer science department. And the computer science department, the background and the mathematical background indeed is much, much weaker than we have in the education. So when they go out looking for jobs, they are labeled as AI, ML kind of people. But if you're doing in the EE and you do the usual communication signal processing, you don't get labeled ML AI, and then you are at a disadvantage of getting a job. And the top of it, a lot of people from our department who have done the PhDs recently, they may do something they get their PhD, but when they go looking for a job, going for Google, basically they're very good at software. Okay, they can pass all their software tests, and they have done one thing for their PhD thesis, published, but when they go work for Google, they're doing totally different stuff, essentially lots and lots of programming, and they spend a lot of time being proficient in doing programming. So.
Thank you. Vince?
Well, first of all, I think, signals and systems is a core part of the EE course, still is, always will be. It's moved down. At least at Princeton, it's a sophomore course now, but I think that part will always be there, I hope. When I spent 10 years as dean, and before that I was director of a center, and I had a couple of sabbaticals on either end. So I was away from teaching for about, 13 or 14 years. And the main graduate course I teach at Princeton is detection and estimation theory. And when I came back from all that, wandering in the wilderness of administration, and taught detection estimation theory for the first time, I taught it like I had taught it before, assuming that the students had fundamentals and stochastic processes and so forth. And it was about halfway through the course till I realized they didn't know a lot of what I was talking about, because they no longer were taking, random processes and that kind of fundamental thing. And now the students are very, very sophisticated when it comes to machine learning and things like that, but really not that sophisticated when it comes to what I would call the fundamentals. And I think that's a real problem. I don't know how to solve it, but I think that's a real problem. And then it's reflected also, I think, in the job students take. I mean, they go to Apple or Google. That's the kind of jobs they're looking for. So, yeah, things have changed dramatically, I think. And it's been driven, of course, by the job market, as it was pointed out. And I don't know what to do about it, but that's an issue, certainly. So.
Petar?
Yeah. These types of jobs have always been, specialized, right? Like Apple and Qualcomm and the rest of the world still does hire, the skill set that you're describing. And even within Google, there are parts of Google that do that algorithm on, I think. But is it everybody? No. I mean, I think maybe the proportion of students graduating to the type of jobs that are available, maybe, no, I think it's okay, may have remained the same. That's all I wanted to say. And of course, the defense industry still continues to hire algorithm development and so on. So.
Right. I just would like to make 3 comments. They're related to curriculum changes in the last 30 years, then how it also reflects on job placement of students. But for the first one, for curriculum changes, obviously we would like to modernize our curriculum, and but sometimes we do it superficially. For instance, our course on detection and estimation theory is renamed to statistical learning, which is not really the same thing, but it sounds for students maybe better, and we attract more students. I had exactly the same impressions. I teach similar courses like detection, estimation, and even machine learning courses, and I found often the preparation of students who take these courses below par and not by little. So this is a big challenge for us who have to teach these courses so that they become meaningful. Otherwise, students seem to be more adapted to use programming, can use somebody else's work, and then use these programs to accomplish something, if it is detection or estimation or machine learning. So this is one thing. Obviously, in the beginning of my career, when I started, the students were much better equipped with the fundamentals than they are now. As for the job placements, before they would go to places, obviously, in telecommunications, in defense, or in consumer electronics. These days, the field is broader. They go to even pharmaceutical companies, finance, healthcare, companies like Google, Apple, and so on. They're very much wanted. So overall, things have changed. It's clear that we also have to change things so that we keep on in pace with the changes in our field.
Well, I'm stuck in the past because for me, it's probability theory, harmonic analysis, linear systems and matrix methods, optimization theory. But importantly, I think for us, it's some appreciation for the constraints of the physical world. We call these things physical laws, but they're actually constraint equations. And if we can teach our kids about these constraint equations, then they can understand or work with people who design sensors. Guess what? Sensors are what produce the data that we A to D convert to then signal process. So it's very important that students have some appreciation for the way the physical world works, the biological world works, maybe the chemical world. So some real serious applied science coupled in with signal processing.
Okay, I would like to make just one more comment. One thing that I did not say was mentoring. Mentoring also changed a little bit. Before, again, it was simply one-on-one communication with students, going on the board, deriving things. But today, students have much more to choose from, including online courses, YouTube information. So it is somewhat different, and it is better for these students. So the only problem is how to get more students who know the fundamentals better.
Can I make one more comment? I'm sorry. We need to tell our students what they'll know and what they can do after each year of their education. So I've always been struck by these portfolio programs by musicians, dancers, visual artists. Visual artists carry around their portfolio under their arm. They used to, now they have a thumb drive. If you're a dancer, you have videos of your dancing. If you're a music student, then you have recordings of recitals you've given. So we need something like a portfolio program where students can show somebody who might want to hire them as a graduate student or hire them as an employee to show that person what they were able to do after their first year. Here's what I did after my first year, my project. Here's what I did after my second year. Here's what I did after my third year. Here's what I did my fourth year. Then you see the progression of the intellectual development and the skill delivery. So something like a portfolio program. What does that do? Well, if you're a department chair, like many people have been here, then your department touts these portfolios from previous students to the parents of incoming students who want their kids to get jobs. Sorry to be so animated.
So yesterday night, Vincent warned me. He's like, what are you talking about time limits and all that? He's like, we are academics and we'll run out of time before we'll run out of questions. It's kind of happening, but I'm looking at Moss and Cheng Dao because they had given me some leeway. I want to figure out how much There's one last question. Should we do or not, or cut it?
One last.
One last? Okay.
Very quick one.
Yes.
How many people take estimation now, and how many people took estimation 15 years ago?
You know, the numbers are not that different.
Oh, they're not
but actually, they came from a lot more a variety of departments. It used to be all electrical engineers. Now it's from all sorts of places, which might explain the background.
But that's good. That's awesome.
Yeah, it's good, but then expectations change.
So the last questions lead is Petar, and we'll apologies for keeping you all waiting from lunch. We'll try to, I guess, panelists will try to be quicker on that. The last question is tied to the previous one, which is related to the fact that one of the reasons that today's generation knows about machine learning or AI is through these computational toolboxes. We have high school students who can actually code in scikit-learn and PyTorch, right? So this AI community has done this open sourcing of these toolboxes, whereas one of the only toolboxes that perhaps we can, at a commercial level, we can point to is perhaps CVX, but that was not production grade either, right? So what has been the role of like production grade computational tools, and how could it be sort of changed in the future that we can actually introduce kids to to signal processing ideas and get them excited? Sanyogita was saying that get excited and then people will change, right? They will move from maybe electronics to signal processing, things like that. So Petar, you want to take it?
I'll share with you my journey. So I was undergraduate student at University of Belgrade, and we had to do a bachelor's thesis. And my bachelor's thesis was a 100% machine learning problem. I had to, using communication signals, find a way to recognize the digital modulation of the signal. And to that end, I was using what was known at the time as modern spectrum estimation methods. And I had to do it on IBM 370 with punch cards. So the way how it worked was and I had to use Fortran. So you write the code, and then you type the punch cards, and then you bring them to someone who would put them through a compiler. And then, of course, in the first round, you had bugs. You had to go back and correct the particular cards. And then at some point, it's done. It works. And then there were devices called plotters. You had to also plot some things. So this was my first interaction with the need of computers for what I had to do. But soon after, I was lucky that we could work on prime computers with terminals. So this was much better than punch cards. And in the late 80s and early 90s, something wonderful happened. Sun workstations came about, and we could use them with MATLAB. That was also very important. That actually accelerated things quite a lot. Fast forward now to this century, obviously things have come to a point where students now use on their laptops GPUs. They have access to clusters of computers on campus or even cloud services and so on, and they could do wonderful things that require lots of computation. So I must say that the thing that and the students realize this, their ability to program and their ability to use all kinds of open source gives them lots of advantage when they look for jobs. And they really put a lot of attention to actually be very fluent in this, which now takes away time from the fundamentals. So, which is why they're much better these days in maybe using software than solving difficult equations or creating something that is really impactful. So overall, things are moving really in direction where the availability of computing resources actually attracts students, and this is something that at least is my impression.
Do you want to? We'll go from that side forward.
I think I'd like to pass the mic on to someone else. Joe Defer here to move things along. I have nothing insightful to add.
Okay.
We're good.
Sanyogita?
Yeah, I think the availability of tools is a good thing, and there'll always be a subset of people who want to go deeper, understand the basics, analytical stuff, and I think that'll expand the pie of the number of people, number of students who get interested in this. So I think it's a good thing.
So thank you so much to the panelists for the we had to limit the conversation for the last two questions, though, but hopefully the lunch would be a good time to continue that conversation. We had some other questions about looking into the future about what may happen. Again, that's a good lunch conversation. I apologize for keeping you waiting from lunch, and we'll conclude here and enjoy the lunch. Thank you. Thank you, Jitendra.
Thank you very much.
Thank you.
Yeah, one.